Hello, physics kids. We want to talk about daily number 7, mechanics number 7. All right, so if you could take mechanics number 7 and get it printed, get it doing whatever you need to do so we can look at it, thank you very much. So we start with Oscar Wilde and his wonderful quote, "We're all in the gutter, but some of us are looking at the stars." I think that's talking about the general human condition and how nobody's perfect, but it's our aspirations that really count. So if you have aspirations, if you're looking at the stars, well, nobody's perfect, but you're better off to be looking up, moving up, thinking where you could go. So anyway, you can interpret that any way you want, but I like that one. Let's look at the first Newton's second law sample problem. I think I want to spell that one out a little bit for you. So let's take a look at that here. And a driver in a car moving at 25 meters per second applies 233 newtons in excess of the frictional force to his car for 1 minute. The car has a mass of 1,400 kilograms, and we want to know what the final velocity is in miles per hour. Okay, so how do we do that? Well, it might be useful to draw a free body diagram on it. And we have 233 newtons in excess of the frictional force. All right, so that's going to be accelerating the car a little bit, right? It's going to be accelerating the car. Do we have some way of finding out what that acceleration is going to be? Well, yes, we do. So if we take givens, the mass we have is 1,400 kilograms. All right, so 1,400 kilograms of mass. The force, which is going to be a net force. What do we mean by net force? Well, this 233 is in excess of the frictional forces. That means that there's no balancing force, so this is an unbalanced force of 233 newtons on a mass of 1,400 kilograms. Okay, let's take a look and see where that goes. The wind was about to knock something over. So anyway, let's take a look and see what that does. The net force is 233 newtons. And if I put all that together, I know I can find acceleration very quickly with the formula F equals ma, mass equal, or force equals mass times acceleration. All right, I want to solve that for A. So divide both sides by m. So A equals force over mass equals 233 newtons over 1,400 kilograms. Now, before we go any further, should we talk about the units? Of course we should talk about the units. How do the units work out? Well, what is a newton? We remember a newton is a kilogram meter per second squared. That means the kilograms drop out. My units are going to be meters per second squared. You can tell that's acceleration. That's just what I'm looking for. Well, when we solve that, what do we get when we solve that? All right, so we get 233 divided by 1,400. We get about 0.17 meters per second squared. We're not done with the problem, but now we know the acceleration. So the car was moving at 25 meters per second. We accelerated it for 1 minute. We want to know what the final velocity is. Okay. So the acceleration equals 0.17 meters per second. The velocity initial is 25 meters per second. Oh, I'm sorry. Acceleration is meters per second squared. If I leave off that second squared, make sure you holler out, right? Acceleration has to be meters per second squared. Meters per second is just a velocity, never an acceleration. All right, we want to know what the final velocity is. The time, can I use 1 minute? No, I can't. So I know that 1 minute is 60 seconds. That's what I'm going to be using. Okay, so I could just put that in. Formula. VF equals VI plus AT, right from your reference tables. VF equals VI plus AT equals 25 meters per second plus parentheses 0.17 meters per second squared times 60 seconds. Now I'm going to use the number that's still in my calculator, all right, which is a little better than the 0.17, and I'll round at the end. Rounding internal to a problem is not nearly as good as rounding at the end of a problem. It kind of makes sense. So times 60 plus 25. So I have 34.985. I have 35.0 meters per second. Notice the second cancels meter per second squared then, so I'm adding meters per second to meters per second, so that works out. All right, so that is that Newton's second law being brought back into our kinematic problems. Newton's second law, we can find acceleration if I have mass and force acting on it, unbalanced force acting on it. So I can easily find acceleration, bring that in. So it's going to be often two-step problems. I think we can handle it. Okay, it's asking you to state Newton's laws. Do that, please. Make sure you state Newton's laws. Know the first two laws. Know them by heart. Now, in a class where I don't suggest memorizing much, why would we know Newton's laws by heart? Are they really that important? Yeah, they're really that important. So know Newton's laws by heart. First law, law of inertia. You could say that, but make sure you know what inertia is. Inertia is directly proportional to, I'll give you a second, mass. What else is it proportional to? Nothing. Mass. If you double the mass, you double the inertia, period. Good. Okay, inertia is proportional to mass. That's Newton's first law. An object in motion tends to stay in motion. An object at rest tends to stay at rest. Okay? Pretty straightforward. More stuff is going to fall here. Forces acting on objects knocks things over. I have a lot of wind blowing outside, and it's knocking some stuff over in the room. An unbalanced force will knock things over. So physics is applied all around us all the time. It's good to pay attention. All right, so we want to talk about now Newton's second law. What is Newton's second law? Mathematically is the easiest way to describe it, and that's simply F equals ma. F equals ma, that gives us a whole new unit. That unit would be newtons, because a newton is a kilogram meter per second squared. Okay, so Newton's second law, F equals ma, force is now measured in newtons. Great, let's talk about tension in elevator problems, shall we? These lend themselves beautifully to free body diagrams, and they're a little bit simpler to figure out than you might anticipate, but we have a 10,000 Newton elevator. So it's 10,000 newtons, and we have 3 800 Newton people standing in it. So that's going to be 10,000 newtons plus 3 times 800 newtons. Okay? You might have seen me do something. You can fuss at me for it. It works out, but you can still fuss at me for it. I wrote down a number without a unit next to it. So why don't I expand that, just so you can see how we would do this. Because sometimes you will tend to write down a number without a unit. But so this would be 3 people times 800 newtons per person. Person and people cancel. So 3 times 800 newtons. But the units still work out. That's important. Okay? So 3 times 800 is 2,400. So we add them together, 12,400 newtons worth of force pulling down. How come the elevator isn't falling to the ground? Well, free body diagram. If we have a force pulling up on it, that's the force applied, that must equal 12,400 newtons going in the up direction. These two forces balance out. Why isn't this object accelerating? Well, because the forces balance out. If there is no leftover force when you add these together, we say it is in equilibrium. If an object is in equilibrium, can it be accelerating? No. All right, so if the elevator starts to move upward at 0.5 meters per second squared, what is the tension in the line? Well, now I have some figuring out to do, because we can use the formula F equals ma to figure out what this would be. But if I want to know how much force I need to add on to accelerate at 0.5 meters per second squared, I have to know the mass. How can I get the mass from this? Well, the mass, we're going to use the formula W equals mg. All right, the weight of the elevator, 12,400 newtons, equals mass times gravity. So W over G equals mass, or 12,400 newtons divided by 9.8 meters per second squared. That will give me the mass of this. So if I have 12,400 and I divide by 9.8, I have 1,265. 1,265 what? Well, a newton turns into a kilogram meter per second squared. Cancels, cancels, so kilograms. So 1,265 kilograms is the mass of this. Great. So if I have a mass of 1,265 kilograms, I want to know what unbalanced force or what extra force I need to. Let's consider what the total force is, and then just do adding the acceleration directly to acceleration due to gravity. So if I am going to do F equals ma and convert that to W equals mg, now my weight is going to equal my 1265 kilograms times 9.8 meters per second squared. Now, if I'm accelerating upward, well, I need to add that onto my 9.8 meters per second squared. After all, ask yourself, if you're in an elevator and you're accelerating upward, wouldn't for a moment while you're accelerating upward, don't you feel heavier? Yes. So you're adding that on. So this is plus 0.5 meters per second squared. Okay? So 1265 plus, I'm using parentheses here, 9.8. I think I messed up. 1265 times, using parentheses, 9.8 plus 0.5, close parentheses. That's 10.3 meters per second squared multiplied by 1265 kilograms gives me, my weight then would be, or the force I need to push up is 13,029.5 newtons. Now, those of you who've been with me for a while, can I write all those numbers, or did I get nonsensical? What's the number I have with the least certainty? Right here. 0.5, how many significant figures in 0.5? There's one significant figure there. So I can't give an answer with a bunch of significant figures when I have such terrible data going in. Not a problem to use terrible data, but a problem to use terrible data and think you have a more precise answer than is justified by your terrible data. So we can say 13,000 newtons, and that would be fine. 13,000 newtons, knowing that the 3 becomes somewhat uncertain. All the numbers after that are nonsensical, so we wouldn't specify any more than that. You could write it in scientific notation if you want to be even more clear about how much accuracy you have there. Well, if we were now accelerating downward at that, how would we change this to accelerate downward? All right, well, you can see all we would do is subtract our acceleration from gravity. Because after all, the floor isn't pushing up as hard on you. That's why you're going down. So in this case then, we have our 1265 times, in parentheses, 9.8 meters per second squared minus 0.5, close parentheses, that's 9.3 meters per second squared. So that equals 11,764.5 newtons. Well, what can I say honestly about that? Well, one significant figure, so the most I can say is 12,000 newtons. So we vary between 13,000 if we want to accelerate up and 12,000 if we want to accelerate down. So that's tension in elevator problems. By the way, if the line snaps and the elevator drops, what's the tension in the line? You think about that one. Okay, let's talk about friction. Should we talk about friction? Let's talk about friction. I had a question when I started driving. I had learned that if I lock my tires up when I'm driving, that with the tires locked, it'll take me longer to stop than with the tires rotating. That never made sense to me. That never made sense to me. How come if the tires lock up, I don't stop faster? It seems to me if the tires are rolling, I'm helping the car move along. So how can I stop faster? Well, obviously, my idea of friction was incomplete. So I want to give you a complete idea of friction. Friction is a force opposing motion between two objects, and it has to be two objects. Here's what's happening. If this is the floor, if this is a microscopic version of the floor, we see the floor is not smooth. We see the floor is not smooth. There's little bumps and scoriations on the floor. There's stuff on the floor. And whatever you're stepping on the floor with, similar that there's bumps on the thing you're stepping on it with. So when these two things interlock like this, you have lateral forces. That means side-to-side forces you can exert. Now, what if the floor was perfectly smooth? Then as you're trying to walk on it, you can't exert any of these lateral forces, and you find very low friction. Floor, in this case, would be very slippery. After they've just polished the floor, in the summertime, they polish the floors very nicely. Then they wax them. How smooth is the floor? Well, you can see a mirror reflection in it. How smooth does it have to be to do that? Very smooth. So how slippery is the floor when it's like that? Obviously very, very slippery. If we have even a little bit of water on the floor like that, the water acts almost like ball bearings, and you can slide quickly and easily in a situation like that. Consider the worst situation for friction, black ice. When you have liquid water, there's surface tension on the water. The molecules are yanking on each other so hard, they stretch out and make a perfectly level surface. If that perfectly level surface should freeze solid, now you have a completely smooth surface that's not liquid anymore. Now it's solid. Black ice. This is what black ice is. When you had liquid water and it freezes solid, there's almost no friction on that. It's one of the most dangerous things you can meet, not just driving, just walking. Black ice can do you in. There's no friction to be had on black ice unless you have something on your feet that can grip through that. And that would be like metal studs on your shoes. Metal studs will cut into the black ice simply because they're harder than ice, so they will cut it and they will grip it. Not much else will. You need studded snow tires to fight black ice. Always a dangerous thing to meet. So think about our friction then. Now maybe we can explain why when tires are rotating, look at the gears, how the tire rotating over a surface grips it, and you can exert lateral force on it. If you start skidding, your tire comes up out of these grooves and you go, and you just scoot over them. So the moment you go into a skid, you have very low friction. And that's usually just preceding your car accident. So if you can keep the tires rolling, you can stop faster. The moment you lock up tires, your car doesn't behave at all the way you think it's going to. Okay? So we have two kinds of friction. We have the unmoving friction. Now, even a tire rotating has this unmoving friction because its gears are locking in. This is called static, unmoving friction. Me standing on the floor, static friction. If I'm trying to move something, when it's not moving, it's static friction. The gears are interlocked. Once I get it moving, you'll hopefully recognize this in what you've seen with real life. Once you get it moving, the gears come up. And now you're just scooting along on top of the gears, so you're lower friction. That's kinetic friction. Kinetic friction is less friction. The formula for friction, let's just hit the formula for friction. The formula for friction is F sub F equals mu F sub n. That's the force of friction equals this quantity, which we'll get to in a second, times the normal force. Now remember, the normal force, when we draw a free body diagram, if an object has weight pushing down and it's on a horizontal surface, the normal force is the force with which the surface is pushing back. So once you know the weight, if it's a level surface, now you know the opposite of the weight, which would be the normal force. It is the normal force, not the weight. You'll see lots of examples where even though you're given the weight, you have to do a calculation for the normal force and it comes out different from what the weight is. And that's anytime we start tipping the surface, right? Normal force now is always being projected out from that tipped surface, so it's no longer going to be equal to the weight. The ultimate example is when you're up on a roof, you realize that your weight is not holding you to the roof. The more the roof is tipped, you have a component of your weight trying to pull you off the roof. Not a good thing. So if F sub F equals mu F sub n, what I want to ask is, what's the units of mu? Now we've talked about every number needs a unit behind it, and I put a big flag on the play if you don't have a unit after every single number, even inside calculations. So you have to have a unit. Units are crazy important in physics. What's the units of mu? So solve for it. How do you solve for this? Well, divide both sides by F sub n. Divide this side by F sub n. What do you get? I'm not worried about a number. I'm not filling in any numbers. I'm wondering about the units. What's the units of force? Newtons. What's the units of force? Newtons. What is a Newton over Newton? Equals 1. So what's the units of mu? There are no units. That's a ratio. Mu is a ratio of the force of friction to the normal force. So in this case, you have a unitless number. Hope you can deal with that. Hope it causes you some problems when you write it down. If it doesn't cause you any problems when you're writing it down, perhaps you are doing physics calculations without units. And I will look over my glasses at you. So that's starting off on friction. Talking about how to do tension in elevator problems, Newton's first and second law. Do the homework problems on it as well. And have yourself just the nicest day. Thank you for paying attention and watching closely here. That was Mechanics number 7. Bye-bye.